So today I'd like to share with you some, not so recent work on trying to use optimal transport to solve strictly correlated electron problems. So this is joint work with my previous postdoc, Yu Hao Kuo, who's recently moved to University of Chicago, and Professor Ling Ling. I think Ling is in the audience from UC Berkeley, and also Michael Lindsay, who's currently at NYU. Michael was Ling's previous student. So because we only have 30 minutes, so I'm mostly going to focus on the work with Yu Hao, and then I'm going to briefly talk about the work with, mention the work that was Ling and also Michael. All right, so here's the outline of the talk. So so the topic of this talk is not directly related to tensor network. So I did some work on tensor network back a few years ago, but it's kind of like old. So I decided to talk about this, give this talk. So I think the main connection is that both in the case of tensor network and here we're trying to approximate very high dimensional functions like wave functions or density matrices, and then this convex relaxation approach hopefully showed you that there's an alternative way to address some of these problems. Okay, so I'm going to start from the first about to tell you what is this multi-marginal optimal transport problems, and then I'll try to spend a few minutes trying to link this with strict correlated electrons. You can see that in some of the cases, strict correlated electrons can be formulated as a multi-marginal optimal transport problem. And finally, I'm going to show you that how do we use convex relaxation to solve these problems in a rather effective way. Okay, so I guess optimal transport is a topic that you probably heard of. So it has gained a lot of attention in pure and applied mathematics over the past 20-30 years. So essentially, the problem is trying to address is the following: in that given two probability distributions, one is rho 1 and the other is rho 2 on a certain space X, and also given a cost function Cxy for X and Y belongs to this space X, what we're trying to do is solve the following so-called optimal transport problems. So you want to find a coupling mu, which is a coupling of these two densities, rho 1, rho 2. So mu is a probability density distribution and live on X cross X. And the projection of, you can think about the mu is right here. And the projection in the first direction is going to give you the density rho 1, and the projection on the second direction is going to be density rho 2. So this is what the definition of a coupling. So you want to find a coupling such that the double integral of the cost multiply these the coupling density mu is as small as possible. Okay, now it's the way we written this way. You can think about after you discretize, this becomes the linear programming problem. So it's in principle this is tractable, and in fact, people do use linear programming to solve that. This is one of the main approaches for solving optimal transport problem. Now, there are quite a few applications of optimal transport. So I guess the initial consideration when back hundreds of years ago, people were thinking about operational research kind of applications. And then over the past few years, there's also topics appear in machine learning, for example, like a generated adversarial network. Optimal transport also appear there as well. Okay, so it is a quite popular topic. Now, in our case, we care about generalization of the optimal transport problem. This is what we call the multi-marginal optimal transport. So here, that instead of giving only two densities, rho 1, rho 2, we are given now a few densities, rho 1, rho 2, all the way to rho n. And each of them is a probability density on this space X. Now, the cost function is, instead of take two variables, now the cost function is going to take n variables. It's going to take variable x1 to xn. And the multi-marginal optimal transport problem is defined in a similar way, is that we're trying to find the coupling mu, but now instead of coupling of two densities, now it's a coupling of n different densities, and such that this like multi-integral, which is the integral of the product of the cost function times this density, is minimized. Okay, so there are a lot of, again, multi-marginal optimal transport problem appear in operational research. for economists, where they're trying to optimize the distribution of the certain resources, these problems appear. Here, I will show you that, in fact, we have a surprising example which comes from many-body shorting equations. And in fact, one problem in many-body shorting equation can also be formulated as a multi-marginal optimal transport problem. Okay, so now we're going to talk a little bit about this connection here. And this is essentially under the topic of the strictly correlated electrons. Now, so the starting point is this many-body shorting equation, where we denoted the Hamiltonian by H. So applied to a wave function psi. Psi is a wave function which takes n different variables. Each of the variables you can think about in the certain physical space. It could be 1D, 2D, or 3D. I mean, usual cases. So therefore, this function is essentially, if you talk about 3D variables, and this is a function defined on an n times 3-dimensional space. So this is really a very high-dimensional function. Now, this wave function is antisymmetric because we're talking about electrons, and we assume that everything is normalized because we want the square of this to be interpreted as a probability density. Now, the many-body shorting equation has Hamiltonian has 3 parts. The first part is the kinetic energy, which is the sum of the minus Laplacian. The second part is a Coulombic interaction, and the last part is the external potentials you put on top of the system. So in this talk, we're going to use K to stand for kinetic, and C to stand for Coulomb, and the V external to stand for the external potential. Now, we have a lot of physicists here, so I don't need to go into details. But we want to compute the ground state energy, and so this boils down to try to minimize this formula. Now, again, as I said, if you have quite a bit of electrons, this is a high-dimensional problem. So, and this is a really high-dimensional tensor. So that's why it's a computation. It's hard problems, and we're here all trying to make some progress on these kind of quantum problems. Now, so one way to solve this is to using this density function theory, which is kind of has been one of the working horses for quantum chemistry. That instead of studying the very high-dimensional wave functions, what we do is that we square the wave function, and then we integrate out all variables except one. So here you see that these x2 to xn, these n-1 variables are integrated out. So what you have left is a function of the one single variable x, and that's what we call density. Now, the DFT approach is try to solve this minimization problem that we have on the previous slide, which is here, which is a minimization over this high-dimensional wave function by 2 steps. So the first step is that you want to find the density rho of a single particle density rho, and then you want to minimize over all the high-dimensional wave function, which give you this electron density rho, and this is the same objective, right? So you formulate the high-dimensional optimization problem into a nested optimization problem. Now, the one thing to figure out is that let's just take a look at this piece, the inner minimization. What one can show is that the inner minimization breaks down to 2 pieces. One piece is involved K plus D, which is the hard part, and the other part involved V external, which is the easy part. So the V external easy part, through a bit of calculation, you see that this actually depends on rho. So therefore, once rho is specified, it's actually, in fact, it's independent of the inner optimization. So therefore, you can just write the V external rho. But the hard part is this is the first piece, which involves both the kinetic energy and also the Coulombic energy. So this is what we denote by F, and in general, this is the unknown universal functional, and so this is what we're trying to interpret, try to approximate. Now, as I said, this F has 2 pieces. One is K and one is C. The K is kinetic, C is Coulombic. And when the K dominates, the typical approach is to approximate this F rho with Kohn-Sham functional. And this is not what we are going to talk about today. And today we care about the case where the Coulombic interaction is dominant and the system is actually strongly correlated. And in this case, what we're going to follow is this so-called strict correlated electron approach. And this is proposed by Seidel about right now more than 20 years ago. So the idea here is that we're going to throw away the kinetic term and only care about this Coulombic term. So here I write down the Coulombic term again, explicitly write it out. Now, because the Coulombic term itself involves the square of the modulus of the wave function, so therefore, instead of writing this in terms of the wave function, I can write this in terms of square mu. So that's why you can formulate this as a high-dimensional optimization problem over this mu. Now, we now realize that mu itself is nothing but the electron, the wave function, the wave function square. So it's electron density over the whole high-dimensional space. So it has to satisfy certain conditions. So the first is that it has to, the projection to each of the dimension each of the particle has to be equal to rho, right? So this is, so you can already see that this is like the multi-marginal optimization problem appearing, because this is a coupling of these rho density, n copies of them. So it's also need to be symmetric, right? And also because it's a square, so this wave function anti-symmetric, but we square it, becomes symmetric. So the integral of this has to be 1 because it's a density in your whole space. Has to be greater than or equal to 0 because it's a density. And also that if you exchange two particles, the wave function has to be 0. So therefore, if you exchange two particles for the mu, and the mu will also be 0 as well, because 0 squared is 0. Now, so you see that this is as I said, this is a multi-marginal optimal transport problem, and where but it's a special multi-marginal optimal transport problem, because the marginal themselves, as actually rho, has to be, all the marginals are the same. So in the previous case, we have rho 1, rho 2, all the way to rho n, so the marginals are different, but here the marginals are the same. So it's somewhat slightly easier problem. But it's also hard because, well, it's hard, okay, but it's special because also the cost function is a little bit special, because previously we have this general cost function, but in this case, the cost function itself is actually can be decomposed into sum of n choose 2 pieces, and each of them is just simply your Coulombic kernel. Okay, so it's a very special multi-marginal optimal transport problem with a special cost. So this cost, I mean, even though it has this decomposable structure, which we're going to use as you will see in 2 minutes, but the problem is that this also is pretty special. It's not like in most of the optimal transport problem, people work with convex kind of cost functions, but here this function is definitely not convex, and so that's also caused quite a bit of problem. In fact, it is one of the main obstacles for using this approach. Okay, now there has been, okay, so now we know that this can be formulated as a multi-marginal optimal transport problem, and let's just try to solve this. So the work that motivate our this project is essentially these 3 papers. So this is an early paper by about it's hard to believe that's almost 10 years ago now. It's by Mendel and Ling. This is from 2012. So they solved this problem in the dual formulation. So they write this optimization problem in dual formulation. So now instead of having exponential number of degree of freedom, because this mu is a high-dimensional tensor, it's exponential degree of freedom in n. What they transfer into exponential number of constraints. So in some sense, they solve the problems, make it a little bit easier in certain cases, but still you have to find this exponential blow up of the degree of freedom or constraints. Now, there's also a few years later, there's this paper by Benamou and Kali and Nella. They use this very popular sinkhole approach. Sinkhole approach is essentially it's an alternating kind of like minimization approach. And it was first applied to optimal transport, but it was soon generalized to these multi-marginal optimal transport. It also has some success on this problem, but again, they have to work with exponential number of variables. So there's 2 years later, there's also this theoretical studies by Garrow and also I think Garrow's student. So they studied the sparsity structure of this multi-marginal solution of the multi-marginal optimal transport. This strongly influenced our work. So the question we ask ourselves is that can we actually solve this multi-marginal optimal transport problem with polynomial complexity? Well, the answer is yes, but we have to approximate it. So the technique we're going to use is something called a convex relaxation techniques, which has become very, very popular in the past decade or so in applied math and also theoretical computer science. And we show that in this paper, how we show that, in fact, we can formulate this strictly correlated electron optimization problems, approximated with convex relaxation, and then get a reasonable lower bound and upper bound. All right. So hopefully so it's a long introduction, and then so hopefully I convince you that optimal multi-marginal optimal transport is appears quite often, and also it's related to quantum mechanics. And now we're going to see that how we're going to use convex optimization to solve that, convex relaxation to solve that. So recall the problem we have is the following: is that this cost function can be written as these and choose two different terms. Each of the term is just Coulombic interaction, and the multi-marginal optimal transport is this problem. Now, so we're gonna do first just try to discretize this problem, because I mean, if you want to put it on a computer, you have to discretize it. So we discretize a space X, which could be 1D, 2D, or 3D, right? Depending on the problem you have, with a grid of, let's say, L points. So L is like a few hundreds or maybe a few thousand. So this is how you discretize your physical domain. So, but L doesn't grow exponentially. It's just a fixed constant. You can think about it to be a fixed constant. Now, and to simplify the notation a little bit, I'll just use lowercase c to stand for the Coulombic potential. So from now on, I'm just only gonna study the discrete version of this continuous problem. So and the integral sign becomes the sum, and I still keep the x. X here stands for continuous variables in my physical space, but here x corresponds to different points on my physical grid. Okay, and here's just transfer the continuous problem to the discrete problem. Oh, okay, so the main idea is that we want to exploit the structure that these cost functions are actually decomposed into terms which depend on only two variables, even though you have quite a bit of them. You have n choose two different terms. So this motivates us to study that if we only care about the cost function depending on two variables, then maybe it's useful to actually look at the two marginals of these high dimensional mu density. Okay. So this picture is trying to illustrate what is the main idea here. So here you have a high dimensional mu, even though it looks like a three-dimensional cube. I mean, I would like to think about this as an n-dimensional cube. Now, what you do is that you take the marginals in any of these KL combinations. So here the 3D, so you take a marginal to be 1, 2, 2, 3, 1, 3, and there's also you can take the other direction to get the G2, 3, for example. Okay. Now, how are we going to use these marginals? Well, more specifically, what we use is that we're gonna try to write our mu in terms of the canonical basis. So mu is a tensor. But here, what I'm doing is just write out each of the element. Okay, where this EX corresponding to these canonical basis, corresponding to different points on the physical space. And so this is really, if you write down the tensor in the element wise, this is how it looks like. Now, we're going to define this, the two marginals for every KL index. So K and L are index going from 1 to n. So for every KL pair, we do the following. So we're iterating through all these entries of my tensor. And for every entry, I form a small L by L matrix, and then I add them together. So this is essentially, if you think about for a second, this is essentially the projection to the two marginals, two of the particles. Now I call it generalized. The reason is because if you care about two particles, you typically K is not equal to L. But here we also allow the special case K is equal to L. So therefore, in the case of the K equal to L, this GKK will just be a matrix where on the diagonal it gives as an L by L matrix. On the diagonal, it's give you the row. Okay, row X. So this is a special case. Now, due to the symmetry, this is the important point. Due to the symmetry, this G tensor. Oh, sorry. Now, after you do the projections, just a matrix. The G L by L matrix. It's the same for. It's independent of K and L as long as K and L are different. And also for different case, it's a GKK, the diagonal. It's not really diagonal, but it's the case where K, the two indices are the same. They will also give you the same matrix, which the epsilon matrix is exactly what I've written down here. And the gamma matrix is something we don't know yet, but this is something that we're trying to optimize, as you will see. Okay. Now the punchline here is that if you take a look at this this problem, is really the only thing that really matters a lot is the two marginals in the objective function. So now let's just try to write the objective function in terms of these two marginals. So this is the original objective function. So one thing I did here is just to reorder the indices. So instead of summing over all possible indices, I sum over pairs. And then for every pairs, KL, I take them out first. And then this only depends on K and L. Then for the rest of the indices, I can sum them up. Okay, so this inner sum is mu. It's just you fix Kn and sum up over the rest of the indices. Now, as you see, the blue term is exactly equal to this G term that we defined. Okay, so in fact, this term, after you sum them up, you get exactly GKL, this matrix, evaluated at the SKXL location. Now, if you take a look at this here, this becomes the trace of the lowercase c and g. So this is become the trace of C and GKL. Both of them are L by L matrices. Okay. Now, then you have to sum over all of the KL. Well, but that's not too hard. You can write it as a bigger trace by introduce a slightly more general notations. So what you do here is that you group all the G's, GIKL matrices into this bigger NL by NL matrices. Right? Each of them is L by L, but K and lowercase l have n different choices. So you get this big NL by NL matrix. Now, as I said from the previous slide, all the diagonals are epsilon, all the off diagonals are gamma matrices. Now you can also do the same thing by generating this C matrix, which is also size NL by NL. And on the diagonal 0, off diagonal is all lowercase c, which is the Coulomb kernel at all my grid points. So once you do that, you see that this original optimization problem can be very compactly written this as a trace of this big C times this big G. Now it's very clean now, but the problem is all the difficulties in this G, which essentially it has to come from a coupling of the rows. Now this is where convex relaxation comes in. And so in the case of convex relaxation, we're going to take a look, what kind of constraints do we have to put on G as a coupling of these rows? Well, these are some of the important necessary conditions. Well, first, the G has to be positive, and G has to be positive definite as well. But the reason why G is positive definite is because you can think about this G as a projection is like some kind of like G can be written. Well, I mean, I don't want to go through the technical form, but G can be think about the mu. I mean, it's not. If you, well, then let me not go into this, but it's straightforward. G is also a positive definite matrix. Now, and the off diagonal, the diagonal entry of G is epsilon, as we said, is diagonal of row. That's what we proved. And also, if you think about the Gij mapped to the all one vector, which is gamma times 1, but this is just a projection of your two marginal to a one dimension, so one particle, and this is actually going to give you rho as well. So these are the conditions that we at least easy to specify. Now you see that I only specify linear constraints and also these positive, semi-positive definite, and also the inequality constraints. So in fact, these are the constraints what we're going to use, because these are the constraints which are easy to specify as constraints for convex optimization problems. So therefore, the main idea is just to relax by dropping all other kind of constraints. I'm only going to work with this set of constraints. So once I do that, I can optimize over my G over all the G's that satisfy these constraints and try to optimize this trace C times capital G. Now, if you take a look at geometric point of view, and what we're really doing here is that this G itself lives in a very high dimensional space. Think about this to be a complicated polytope with exponential number of constraints. But what we do is that we project it and down, and for the projection lowercase, this capital G, it becomes a polytope with only polynomial number of constraints. It's really not a polytope because we have the semi-definite constraint, but it's useful to think about this one. Okay. Now, so this is what we're going to do. You can just go ahead and solve this on computer, but the final step, what we actually did is that we actually rewrite a little bit by introducing another matrix. Instead of work with gamma and epsilon, we work with something called delta. So for the sake of time, to save some time, I'm just going to skip this, but I want to convince you that at the end, we have this convex relaxation problem, which only involves trying to optimize this N by L matrix delta. So if L is like 1,000, so you can think about this really optimized over 1,000 by 1,000 matrix, and it's a semi-definite, positive semi-definite matrix. So it's something that typical SDP software can handle.
I think you have about 4 more minutes. I just want to give you one.
Okay, sure. Yeah, I can wrap this up in 4 minutes. So now, why do we expect this relaxation to be reasonable? This is really motivated by this paper by Garrow about a few years ago. And what they said what they showed is that the extreme points of these N-representable symmetric two marginals is meaning that these G's that coming from the projection of these high dimensional densities is the extreme points is given here. Okay, so you can think about this extreme points right here on this figure. So what we showed is a theorem based on which you diverged their results is we showed that in fact this set of gamma, the extreme points, is actually live on the extreme, is actually part of the extreme points of the convex set we're optimized over with. So therefore these black points is also live on the boundary of the set we're optimizing. Okay, even though it has much cheaper description, right? It's only polynomial number of degree-free constraints. So does this give you some confidence? Because even though we relax the problem, we didn't relax it too much because the original boundary points is also the extreme points is also my new extreme points. Now here I only told you that this projection to two marginals, but we can also project to three marginals. And in fact, by using a three marginal projection, using this algorithm called the Generici algorithm, which you heard about in the tutorial of this semester program, we can actually get an upper bound for this strictly correlated electron energy. So we also, and this is also most of the work done by Yu Hao and Ling and also Michael, that this can be also extended to the second quantization case, but let me not get into this. So let me just show you a few numerical examples. So here, just a simple 1D case where we can use very refined grid. It's 1,600 grid points. And we consider 1D problem going from -2 to 2. And this is my density. It's roughly look like a Gaussian. And so if you solve for this gamma, you remember this gamma is this two marginal, right? So if you solve the gamma, you see that this is how the gamma look like. It's so you see that on the diagonal it's 0. There's no density. And actually, once you give one electron location, the rest of electrons 1, 2, 3, 4, 5, 6, 7 is well separated, and they are trying to repel each other. And so you can see that, in fact, it's not easy to guess this kind of picture. You can, if you have a lot of physics intuition, you might be able to do it. But in general, I mean, so it's not so easy to get such a picture. And also, I mentioned earlier that the support of this density mu is very singular. And in fact, you can see from this picture here, the rho actually have very singular support. Okay, even though, sorry, the gamma has very singular support, even rho does not have. Now, okay, so I also have a few more other numerical examples. So this compares with that with a little bit low resolution, we can actually show the comparison between the two marginal, three marginals, but I didn't get into the details of this discussion of three marginals, but I just want to show that there's something called a relative gap, because the two marginal give us a lower bound, so upper bound, the three marginals give a lower bound. So in fact, the true ground state energy is actually between these two numbers. So therefore, this allows us a way to have an estimate about how accurate we are. Right. So in fact, the relative gap can be pretty small at 10 to the -6 for the simple examples. Now, again, this is a 2D example, which is a little bit harder. So this tells you that if I have a uniform density, what would my gamma look like? Here, I just showed you the case where I fix one electron and show you where the other 4 electrons going to look like. So they're actually quite spread out. Okay. So again, finally, I would like to, so this is all I have. And it's a convex relaxation approach to solve the strictly correlated electron problems. So it's, I mean, this is not directly related to tensor network, but this is, I feel like this is another orthogonal direction where, I mean, where for certain problems like this one can also bring us some fairly useful low complexity algorithms. So with that, I conclude and thank you very much.